Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Glad to be back diving into this stuff.
So I want you to imagine something for a second. You're sitting in a window seat at 30,000 feet, right?
Oh boy, okay.
And the jet engine right outside your window suddenly crosses this totally invisible aerodynamic threshold.
Just bam, out of nowhere.
Exactly. Within milliseconds, the airflow reverses. Just a catastrophic surge of pressure violently blasts right out the front of the intake.
Terrifying scenario, honestly.
Right. Now scale that way, way down. Imagine standing in an office and you're fighting with a printer that inexplicably jams and, crumples your paper every third time you try to print.
A different kind of terrifying, but yeah, deeply frustrating.
Yeah, totally. At first glance, a jet engine exploding and a paper jam seem completely unrelated.
Worlds apart, you would think.
Yeah. But for those of us who design and build the physical world, hardware geeks, mechanical designers, they fundamentally come down to the exact same invisible architecture.
They absolutely do. It's all the same underlying physics.
So our mission for this deep dive is to really get to the heart of what it means to be a creator of physical things.
To really look under the hood.
Yeah. We're exploring the hidden framework of mechanical design, systems engineering, and motion control.
The real brawn of the machines.
Exactly. We are asking how engineers actually translate abstract human needs into dynamic, self-regulating physical machines. Machines that don't just, tear themselves apart the second you turn them on.
Right, which is harder than it sounds.
Yeah.
And to do that, we brought a serious stack of sources today.
Oh, yeah, we are heavily armed today. We've got a pile of intense MIT systems engineering lectures.
Some really deep readings on critical parameter management.
And a bunch of mathematical models covering dynamic physical systems and controls. So if you want the ultimate shortcut to bridging the gap between a nice, clean CAD drawing and a machine that actually works in the messy real world, you are in the right place.
Yeah, because we had to strip away that illusion, right? The illusion of the pristine, mathematically perfect computer model.
The CAD lies to you.
It totally lies.
Yeah.
To really answer how machines survive, we have to wade into the vibrating, chaotic reality of physical parts.
The brawn.
The brawn, exactly. We're going to look at managing high-impact forces, transforming energy, all of it.
But before we even get to cutting metal, right? Before the gears and the hydraulics.
We have to confront the blueprint, the foundation.
Because the gap between a concept and a functional machine is notoriously treacherous. Most ambitious hardware projects, they don't fail because someone forgot how to calculate a bending moment.
No. They fail because the system was trying to solve the completely wrong physical problem from day one.
Which puts us squarely in the domain of requirements engineering.
And I know. To a lot of hardware folks, the word requirements sounds like suspicious corporate bureaucracy.
Oh, 100%. It sounds like a boring Word document some project manager demands before the real engineers get to play in the machine shop.
Right, but when you look at high-performance architecture, engineering those requirements is literally the foundation.
It's just as structural as the titanium you end up using.
Exactly. If the foundation is flawed, the machine fails, no matter how beautifully you machined the parts.
So you can't just hand a designer a sticky note that says, make it fast and user-friendly.
No, that's a disaster waiting to happen. A well-architected requirement has to have very specific, rigorous attributes. There are rules here.
Let's break those down. First rule, a requirement must be necessary.
Which brings up a brilliant diagnostic question for any design team. You just ask, what happens if we delete this requirement entirely?
Right, and if the answer is nothing, or, the user wouldn't even care, then it's not a requirement.
You've written a preference. You're gold-plating the design.
You're just adding manufacturing cost and testing time for zero functional benefit.
Exactly. Okay, so second rule, the requirement must be verifiable. And this is where ambiguous language completely destroys projects.
Oh, the vague language is a killer.
If you write, the system shall be reliable, you've failed. That's a terrible requirement.
Because how do you test reliable, right? Does that mean it runs for 10 hours, 10,000 hours?
Exactly. If you can't prove it's been met through a physical test, an inspection, or a hard analytical model, it is useless to the engineering team.
So how should you write it?
You write something like, the system shall operate for 5,000 continuous hours under a thermal load of 50 degrees Celsius with 0 critical faults.
Ah, okay. Now the testing department knows exactly what physical reality they have to go prove.
Right. And the third rule is that it must be attainable. I mean, it has to exist within the laws of physics in your project budget.
No anti-gravity machines, unfortunately.
Sadly, no. But the semantic rigidity of all this is what's really fascinating.
Yeah, the language itself is engineered to remove human ambiguity. You don't use synonyms just to make the document sound pretty.
No, there are strict legal and engineering weights to specific words, like the word shall.
The system shall weigh under 10 kilograms.
Right, that is a non-negotiable physical constraint. It's law.
But what if you're just describing the environment?
Then you use will. Like, the system will operate in a vacuum.
Yeah.
It's just stating a factual condition.
And if it's a nice-to-have target?
Then you use should. It's desired, but not mandatory for baseline success.
Okay, so those linguistic boundaries, they form the whole contract for the development cycle.
They do, but that contract is only step one.
Right, because once you know what the machine shall do, you have to define the physics of how it's actually going to pull it off.
And this introduces a profound distinction.
Mm-hmm.
This actually came out of Xerox's engineering divisions back in the 1970s.
The difference between a critical parameter and a critical specification.
Yes. And I suspect most people throw those terms around like they mean the exact same thing.
Oh, absolutely. They assume a parameter and a spec are just two different ways to talk about a dimension on a blueprint.
But they're fundamentally different, and mixing them up is a huge cause of machines failing in the field.
Okay, lay it out for us. What's the difference?
A critical parameter is the functional variable that controls the pure physics or chemistry or thermodynamics of the system. It's the unyielding reality required for the thing to work.
And the critical specification.
That's the highly specific, human-chosen detail that goes onto manufacturing drawing to try and physically create that parameter.
Okay, let's ground this. Let's go back to that Xerox paper feeder mechanism we joked about.
Perfect example. Everyone listening has fought with a printer grabbing 3 sheets of paper at once.
Oh, the worst.
So to feed paper flawlessly, Xerox engineers empirically tested it and found the feed belt needs to exert exactly 15 newtons of tension on the paper stack.
15 newtons. So that physical force, that is the critical parameter.
Exactly. And here's the catch. You will almost never see 15 newtons stamped on the actual part drawing sent to the machine shop.
Right, because the machinist doesn't make newtons. The machinist makes parts.
Exactly. What the machinist sees are the critical specifications. They see a drawing for a cold-rolled steel bracket with specific angles,
They see a roller that needs to be exactly 20 millimeters in diameter.
and a coil spring with a very precise spring rate and wire thickness.
So the designer chose those specific dimensions and materials so that when you bolt it all together, the resulting force happens to be 15 newtons.
Right.
Okay, let me push back on this a bit. Let's unpack this. Isn't it enough to just put tight tolerances on the CAD drawing?
What do you mean?
Why do we need this whole separate philosophical layer of parameters versus specs? If the spring and the bracket make 15 newtons, just make the spring and bracket right.
Because the detail designer, the person living inside the CAD software every day, they are operating in a really hostile trade-off space. They aren't just thinking about the 15 newtons. They're actively fighting a war against manufacturing costs.
Oh, right. Budgets.
Budgets, assembly line ergonomics, safety regulations, weight limits. It is so loud with competing demands.
So they get distracted.
Exactly. It's incredibly easy for a designer to say, hey, if I tweak the shape of this bracket, I can make it 10 cents cheaper to stamp out a sheet metal.
But in doing that, they slightly alter the anchor point for the spring.
Yes.
Yeah.
They hit their cost target, their boss is happy, but they accidentally drop the tension to 12 newtons.
Wow. And the machine shop just blindly produces the cheaper bracket perfectly to the new spec.
Yep. Quality control measures it, says matches the CAD drawing perfectly, but the core physics have been compromised.
And now the printer jams in the field.
Exactly. That's why the critical parameter drawing exists. It sits above all those daily manufacturing compromises.
It's like a beacon.
A totally unyielding beacon. It says, redesign this bracket 50 different ways if you want to save money, but you must mathematically prove you still deliver exactly 15 newtons.
So you don't lose sight of the physics, but let's look at the manufacturing side of this.
Okay, let's go to the factory floor.
Say we respect the 15 newtons. We design the perfect bracket, perfect spring. We slap incredibly tight tolerances on the drawing, plus or minus 0.01 millimeters.
Right.
Doesn't that guarantee the physics if we just demand absolute perfection from the factory?
And that assumption leads directly into the great myth of mechanical engineering.
The myth of perfect parts.
Exactly. You can type whatever microscopic tolerance you want into a computer, But eventually, a physical cutting tool has to shear physical steel.
And things get messy.
Very messy. The tool wears down with every single pass. The temperature of the factory floor causes the metal to expand and contract.
The spindle vibrates and creates chatter.
Right. The reality is, no two manufactured parts in the history of human industry have ever been absolutely identical.
And the history of how we actually deal with that imperfection is basically the history of mass production itself, isn't it?
It really is. Before the late 18th century, formal tolerances didn't even exist. Everything was bespoke.
Like a master gunsmith forging a trigger mechanism and just hand filing it until it fit perfectly into one specific wooden stock.
Exactly. It worked great, but from a systems perspective, a total logistical nightmare.
Because if that musket broke on the battlefield, you couldn't just swap in a trigger from a different dead musket.
No, the parts were entirely unique to the assembly.
So it was actually a French artillery general, Jean-Baptiste de Gribeauval, back around 1765, who realized this was a problem for military dominance.
He needed field repairability, interchangeable parts for cannons and muskets. Any wheel had to fit any carriage.
But the technology of the time just rebelled against the idea, right?
Oh, completely. It took decades of brutal trial and error. It moved through the American armories, places like Harper's Ferry, all the way to Henry Ford's assembly lines to really figure it out.
And the way they finally enforced that interchangeability was this rigid, gonna-go gauging culture.
Yes. And that birthed the modern engineering obsession with binary tolerances.
Right, so you design a shaft. Nominal target is 25 millimeters. You assign a tolerance of plus or minus 0.025.
And you hand the machinist two steel blocks, one with a slightly larger hole, the go gauge, one with a slightly smaller hole, the no-go gauge.
If the shaft fits through the first, but gets stuck on the second, it's perfectly good.
But if it fails either, it's completely bad. It's an absolute cliff edge mentality.
And that binary cliff edge creates massive friction between departments, doesn't it?
Oh, total warfare. The design engineer is terrified of failure, so they slap the tightest possible tolerance on the drawing.
And the manufacturing engineer sees it and screams because hitting that precision requires painfully slow, expensive machining.
And they just fight over where to place that arbitrary cliff.
So how do we get past this binary war?
The paradigm shift came from Dr. Junichi Taguchi.
The Taguchi shift.
Right. Taguchi recognized that the go-no-go cliff was an economic lie. Quality isn't a cliff. It's a gradient of degradation.
So you shouldn't just pick a tight tolerance out of thin air to feel safe.
No. You select your manufacturing process and tolerances by minimizing the total mathematical cost to society.
And total cost isn't just the hourly rate of the lathe operator, right?
Not at all. It's production cost plus the hidden deferred quality loss caused by variation out in the field.
And the math Taguchi developed to model this is so elegant. Let's really break down the mechanics of his quality loss function.
Let's do it. So we write it out as L equals L sub C multiplied by the square of the fraction delta over delta sub C.
Okay, let's define those variables. L is the expected quality loss.
Right, that's the quantifiable economic pain caused when a part deviates from perfect nominal target.
And L sub C.
That is the financial loss incurred at the customer's tolerance limit. It's the hard cost of a severe countermeasure.
Like sending a tech on a plane to fix a jammed printer, replacing warranty parts, the damage to your brand reputation, big numbers.
Usually very big numbers.
Then we have the denominator inside the parentheses, delta sub C.
That's the customer's tolerance.
Yeah.
The physical threshold where the machine degrades so badly, the customer actually notices and demands a repair.
And finally, the numerator, delta.
That is the actual physical deviation of the specific part you just pulled off the line compared to the perfect target.
And the absolute genius of Taguchi's insight is the square of that fraction.
Yes. Because it's squared, the economic pain doesn't scale linearly as you drift from perfection.
It grows exponentially, like a parabola.
Exactly. If you are twice as far from perfect, you are causing 4 times as much hidden economic damage.
This math completely destroys the traditional go-no-go mindset.
It shatters it. Under the old system, if your boundary is 10 units, a part that deviates by 9.9 is tossed in the good bin and shipped.
While a part at 10.1 goes in the scrap bin.
Right, but Taguchi's parabola proves that the 9.9 part is not good.
It's already causing a massive, invisible quality loss. Accelerated wear, noise, performance drops long before it breaks.
Which forces a completely new approach. 3-tiered tolerances.
Okay, walk me through the 3 tiers.
The widest boundary is the customer tolerance, that delta sub C. Hit this, and the machine is functionally unacceptable to the user.
Tighter than that, inside the customer boundary, is the manufacturing tolerance.
And its placement isn't arbitrary. It's dictated by the economics of the loss function.
Because it's exponentially cheaper to scrap a slightly bad part in your own factory than to wait for it to trigger that massive L sub C cost in the field.
Exactly. You shrink the factory tolerance to catch variation before it gets on a shipping truck.
And tighter still, sitting right around the perfect nominal target, is the adjustment limit.
That's your operational boundary on the active factory floor.
So if a machine tool starts drifting toward the adjustment limit due to, say, thermal expansion,
You stop the line. You recalibrate back to dead center. You do not wait for it to hit the manufacturing tolerance.
here's where it gets really interesting for me. It's exactly like adjusting your car's alignment.
Oh, that's a perfect analogy.
Think about it. The adjustment limit is a technician noticing a microscopic drift on the assembly line and tweaking a tie rod for a few bucks.
Barely costs anything.
Right. Then the manufacturing tolerance is the final inspector at the plant, realizing the steering wheel is crooked, requiring an hour of labor to pull the car aside and fix it.
Much more expensive, but still contained in the factory.
Exactly. But the customer tolerance, that's the driver, 8 months later, furious on the side of the highway with 4 completely bald, ruined tires and a vibrating suspension, demanding thousands in warranty repairs.
It's a cascading failure of costs.
Taguchi proves that catching the variation early, hunting down that drift at the adjustment level, is exponentially cheaper. It's not just obsessive engineering.
Mathematically, it is the cheapest way to build a machine. And it changes how you buy factory equipment, too. You don't just ask if a cheap lathe can barely hit the tolerance. You run the expected variation of the cheap lathe through Taguchi's parabola.
Oh, and then you compare it to a crazy expensive, ultra-precise grinder.
Exactly. If the expensive grinder keeps parts closer to nominal, the massive reduction in field warranty costs might literally pay for the machine in 6 months.
You're engineering the economics of precision itself.
Precisely.
But let me play devil's advocate here. Let's look at the dark side of this.
Okay, let's hear it.
We can engineer the critical parameters perfectly. We buy the multi-million-dollar grinders, use Taguchi's math, minimize variation, but we're still building physical objects subjected to extreme forces, thermal shock, the real world.
The real world is undefeated.
Right. Machines will get pushed past their limits, aerodynamics will fail. So when precision isn't enough, what do we do?
When precision fails, we transition into a philosophy I like to call engineering jujitsu.
Engineering jujitsu, I love that term. What does it mean in practice?
It means designing mechanisms that actually anticipate an inevitable physical failure.
And instead of building a massive wall to brute force against it.
Exactly. Instead of a wall, you use the kinetic energy, or changing physics of the failing state itself, to shift the machine into a secondary safe operating mode.
So you're defining a twin operating mode. If you can't avoid the danger zone, you build a mechanical trapdoor to sidestep it.
That's the perfect way to visualize it. And the case studies here are incredible. Let's go back to that jet engine compressor surge we talked about at the start.
Okay, setting the scene again. A compressor surge is insanely violent, right?
One of the most violent aerodynamic events a machine can experience. Inside the intake, you have these multiple stages of spinning compressor blades.
Which are essentially a rotating annulus of tiny airfoils spinning at tens of thousands of RPMs.
Ramming incoming air backward into smaller and smaller volumes, building massive pressure for combustion.
But just like an airplane wing, those blades rely on smooth, attached airflow.
Right. And if the angle attack gets too steep or the mass flow of air drops suddenly, maybe from a crazy maneuver, the boundary layer of air separates.
The blades aerodynamically stall.
And when they stall, they lose their grip on the air. But the pressure behind them is immensely high.
So the moment they lose pumping authority, that high-pressure air violently reverses direction.
It blasts forward through the compressor. Huge vibrational shock, massive temperature spikes. It can literally tear titanium blades right off the rotor hub.
And engineers plot this on a map, creating a strict surge line, right? If you cross the line, the engine destroys itself.
Exactly. So in 1978, a patent was filed for a purely passive mechanical design that uses the physics of the stall to actually prevent the surge.
Engineering jujitsu, what did they do?
They machined a series of specific angled slots into the static outer casing of the compressor, directly above the tips of the spinning rotor blades.
How does that create a twin operating mode?
Well, during normal, healthy operation, the high-velocity air flows straight through the engine actually. The slots just sit there doing nothing.
But when a stall begins to form,
When that boundary layer starts breaking down, it creates a localized zone of high-pressure turbulent air right at the tips of the blades.
And here's the jujitsu moment. That localized high pressure is violently forced up into those angled casing slots.
Yes. The slots bleed that specific turbulent pressure off, route it slightly forward, and re-inject it into the main airflow.
It literally deflates the high-pressure bubble of the stall before it can cascade into a full surge.
It uses the changing pressure of the failure mode to activate the safety mechanism. No moving parts, no digital sensors.
And how much did that expand the surge margin?
By a staggering 20%.
That is wild. Just purely passive mechanical brilliance.
Right. Now, the second case study applies this exact same philosophy to something much more mundane. Our favorite Xerox paper feeder.
Back to the printer. We already know the critical parameter is 15 newtons of tension,
But the feeder still has to handle the severe failure mode, the multi-feed.
where 2 or 3 sheets stick together and get pulled in at once.
Exactly. Now, standard design architecture uses two components to fight this. On top, you have the driven feed belt pulling the top sheet forward.
And underneath the stack, you have the retard roll.
Right. The retard roll pushes backward, applying a counterforce to hold the lower sheets in place while the top one slides off.
Because the microscopic friction between the sheets of paper is often too strong, dragging the second sheet along.
Precisely. But let's look at the wear physics of normal, successful single-sheet operation.
Okay.
The powerful feed belt yanks a single sheet forward. That paper is being dragged aggressively across the surface of the stationary retard roll.
And paper is surprisingly abrasive, isn't it?
Very. Over thousands of cycles, that sliding friction acts like sandpaper. It wears the surface of the retard roll flat.
Friction coefficient drops, and boom, it can't hold back the second sheet anymore. You get multi-feeds.
The primary failure mode is directly caused by normal, successful operation. The machine destroys itself just by working perfectly.
So what's the jujitsu solution? How do they fix it?
In 1984, they invented a twin operating mode by installing a drag brake internally, right inside the core of the retard roll itself.
Okay, map out the forces for me.
The drag brake requires a specific amount of torque to slip. When pulling a single sheet, the friction of the rubber feed belt on paper transfers a massive amount of force.
High enough to overpower that internal drag brake.
Easily. So during normal single-sheet feeds, the retard roll doesn't sit still and get sanded down. It actually spins forward with the paper.
Because they're moving at the same speed, there's no relative sliding friction. The wear drops to virtually zero.
Exactly. But what happens when two sheets of paper try to sneak through?
The interface changes. Friction between paper on paper is way lower than rubber on paper.
Right. So when that slippery paper-on-paper interface hits the retard roll, it can't transmit enough force to overpower the internal drag brake.
The force is too low, so the brake remains engaged.
The retard roll instantly stops spinning, locks up, and becomes a stationary wall of friction that holds the second sheet back.
Unbelievable. So what this means for the designer? It sounds like mechanical martial arts, using the failure's own energy against it.
It absolutely is.
But how do you anticipate these hybrid-specific physical failures before you've even built a prototype? You can't just guess how much torque that brake should have.
You definitely can't guess. You have to mathematically model the energy transfer before any metal is cut or rubber is molded.
Which means transitioning from mechanical tricks to the rigorous mathematical language of dynamics.
Right. To anticipate these states, we have to learn to read the code of the physical universe.
And that code breaks all physical energetic systems down into two fundamental types of variables, right? Through variables and across variables.
Yes. This framework is essentially a universal Rosetta Stone for engineers.
It's the realization that mechanical, electrical, and fluid systems aren't actually distinct disciplines. They are mathematically identical.
Exactly. Let's start with through variables. This represents a quantity physically transmitted through an element. You measure it by cutting the system open and seeing what flows past.
So in a mechanical linear system, the through variable is physical force.
In a rotational system, it's torque. In an electrical circuit, it's current flowing through a wire.
And in a hydraulic system, it's the volumetric flow rate of the fluid moving through a pipe.
Right. Conversely, an across variable is a difference in state measured across an element. You probe two distinct points and compare them.
So for our linear mechanical system, the across variable is the velocity difference between two ends of a shock absorber.
In rotational mechanics, angular velocity difference. In electrical, the voltage drop across a resistor.
And fluid dynamics.
Pressure differential between the inlet and outlet of a valve.
So through and across variables are basically the Rosetta Stone. Water flow and pressure is mathematically identical to electrical current and voltage, or mechanical force and velocity.
It's beautiful, isn't it? A mechanical spring storing force is mathematically identical to an electrical capacitor storing charge.
Once you learn the math, you can model any physical reality. You could draw an electrical circuit to simulate a truck's bouncy suspension.
You literally could. And because the architecture is unified, we categorize the components that manipulate these variables into two groups: transformers and transducers.
Okay, let's differentiate those. The transformer modifies energy while staying entirely within the same physical medium, right?
Exactly. A mechanical lever is a transformer. It takes a small force over a large distance, turns it into a massive force over a tiny distance. Still linear mechanics.
A gearbox does the exact same thing for rotational torque and speed. An electrical transformer steps up AC voltage while stepping down current.
All staying in their own domains. But a transducer bridges the domains. It converts energy from one physical medium into a completely different one.
Like a DC motor.
Right. It's a rotary transducer. Accepts electrical current and voltage, outputs mechanical torque and angular velocity.
A piezoelectric crystal takes physical compression force and outputs an electrical spark. A hydraulic piston takes fluid flow and turns it into linear mechanical force.
We link these transformers and transducers together using through and across variables to build a dynamic system model.
But systems behave differently depending on how they store energy, right? That defines the order of the system.
Yes, the simplest is a first-order system. It only have one type of energy storage element.
Like a hot cup of coffee slowly dissipating heat into a room.
Perfect example. Or a boat moving through water. The mass of the boat stores kinetic energy, and fluid drag just bleeds it away.
And mathematically, a first-order system is defined by its time constant, tau.
Right. Tau dictates exactly how fast the system responds to a change.
But the crucial behavior here is that it always approaches its final steady state monotonically, right?
Exactly. If you hit the throttle on that boat, the speed smoothly rises until it hits top speed. It never surges past the top speed, slows down, and speeds back up.
No bouncing, no oscillation, just a smooth glide to the limit.
But the moment you introduce a second type of energy storage,
Chaos enters the chat.
total chaos.
Hmm.
If a system has two independent energy storage elements, like a mechanical system with both a mass storing kinetic energy and a spring storing potential energy, it becomes a second-order system.
And they are dramatically more complex because the energy violently sloshes back and forth between the two storage elements.
The mass stretches the spring, turning kinetic into potential energy. Then the spring snaps back, transferring it back to kinetic in the mass.
Which introduces oscillation, bouncing.
Mathematically governed by two parameters: the natural frequency, omega sub n, and the damping ratio, zeta.
Natural frequency is just the inherent speed the energy wants to slosh at, right? Like striking a tuning fork.
Exactly. And the damping ratio, zeta, measures how quickly the system bleeds that sloshing energy away through friction or heat.
And by looking at zeta, we can predict 4 distinct physical behaviors. Let's walk through them.
Okay, first behavior. If zeta is greater than 1, the system is overdamped,
Meaning the friction is so dominant it kills all oscillation.
very sluggish. It slowly creeps toward its target and never overshoots, like a heavy glass door with a really strong pneumatic closer that takes forever to swing shut.
Overdamped, got it. What if we tune zeta to equal exactly 1?
That's a critically damped system.
Oh.
In motion control, this is the holy grail.
Because it's the absolute fastest possible response time without any overshoot.
Right. A robotic arm snaps to its exact coordinate and stops dead, perfectly still.
But if zeta drops between 0 and 1,
Then it's underdamped. And this gets violent. It responds incredibly fast, but the mass carries so much kinetic energy it blows right past the target,
and the spring yanks it back, causing it to overshoot the other way.
oscillating back and forth, slowly decaying. Think of a car with blown shock absorbers bouncing up and down 5 times after you push on the bumper.
It has the spring energy, but lacks the damping ratio to bleed it off quickly.
Exactly. And the final extreme, if zeta equals exactly 0,
Absolute no damping. A harmonic oscillator.
a frictionless pendulum in a vacuum,
Yeah.
endlessly trading kinetic and potential energy at its natural frequency until the end of time.
Okay, so we've mapped the physics, we understand requirements, Taguchi tolerances, jujitsu traps, dynamic models.
But an overdamped mass on a spring just sits there. It has no agency.
Right. To make it useful, we have to impose our will. We measure its state, calculate the error, and force it to comply.
We are transitioning from the mechanical brawn to the digital brains, feedback loops, and control architecture.
A closed-loop control system relies on three pillars of hardware: sensors to measure reality, a control algorithm to calculate the error, and actuators to apply physical brawn.
Let's start with sensors. How does a computer perceive motion?
For highly precise linear displacement, I know the LVDT is the gold standard, linear variable differential transformer.
It's so elegant because it relies entirely on the geometry of magnetic fields. No physical friction to wear out.
How is it built?
It's a hollow cylindrical tube with three distinct coils of wire inside. A primary coil dead center and two secondary coils flanking it, wired in series opposition.
And you attach a magnetic core to the object you want to track and let it slide inside the tube.
Right. We energize the central primary coil with an AC excitation voltage, generating an alternating magnetic field.
As the core slides, it alters how that magnetic flux links with the two secondary coils.
Exactly. When it's perfectly centered, the flux is equally divided. Because they're wired in opposition, their induced voltages cancel out. Zero reading.
But the microsecond that core moves left.
The magnetic coupling shifts. The left coil generates more voltage than the right. By demodulating that differential, the computer gets a precise, continuous analog signal of position.
Amazing, but that's linear. For rotary motion, spinning motors, and robotic joints, you use an optical encoder.
The industry standard. Imagine a glass or metal disc attached to a spinning shaft with thousands of microscopic, transparent, and opaque lines printed on the edge.
An LED shines through it, and a photodetector sits on the other side.
As it spins, the opaque lines interrupt the light. On, off, on, off. The computer counts the pulse frequency to know the speed.
But speed isn't enough, right? A robotic arm needs to know direction. Is it moving up or down?
Right, which is why optical encoders use a technique called quadrature.
They print two concentric tracks of lines, offset by 90 degrees of phase.
With a sensor on each track, one sensor always sees the light slightly before the other.
So if sensor A pulses before sensor B, it's spinning clockwise. B before A, counterclockwise.
Combining quadrature with highline counts, a standard absolute encoder can slice a single rotation into over 65,000 distinct positions.
Okay, sensors are handled. Perfect map of reality. Now the brain needs to push back with actuators. We've got standard DC motors using magnetic fields for rotary torque.
But when you need thousands of pounds of instantaneous force, you leave electricity behind, you use fluid power, hydraulics, and pneumatics.
Hydraulic actuators use highly pressurized, incompressible oil. How does the brain control all that brawn?
Using a spool valve. Imagine a solid steel cylinder, the spool sliding inside a closely fitted sleeve.
The sleeve has ports connected to a massive power piston.
As the spool slides, it uncovers ports, allowing high-pressure oil to rush into the piston, driving it with immense force.
But the internal geometry of that spool dictates everything. The sections blocking the fluid are called lands, right?
Yes. If the solid land is physically wider than the port it covers, the valve is overlapped.
Which is fine for cheap manual equipment like a tractor loader so it doesn't leak, but for digital control.
An overlapped valve is a nightmare for digital control. It creates a mechanical dead zone.
Because the computer commands movement, the spool shifts a millimeter, but the port remains blocked.
The computer's screaming for action, but the machine ignores it until it clears the overlap. It makes the math unstable.
So aerospace and robotics use underlapped valves instead.
Right. The solid land is actually machined slightly narrower than the port.
Meaning even in absolute neutral dead center, a microscopic amount of high-pressure oil is actively leaking past the edges into both sides of the piston.
It wastes a little energy, but the trade-off is total sensitivity. The microsecond the spool moves, pressure changes instantly. No dead zone at all.
The brawn reacts perfectly. What about pneumatic systems? Compressible air instead of oil.
You lose the crushing power but gain incredible speed. And no risk of oil fires, so chemical plants love them.
A really cool actuator here is the pneumatic nozzle flapper. It's a mechanical amplifier.
Converts a tiny microscopic displacement into a massive change in air pressure. The architecture is just a tiny restrictor nozzle blasting continuous pressurized air into the atmosphere.
And a flat piece of metal, the flapper, mounted on a pivot right in front of the nozzle.
The control algorithm uses a tiny electromagnet to move that flapper. Move it a fraction of a millimeter closer, it restricts the escaping air.
And the back pressure in the pipe skyrockets instantly.
The dynamic equation governing this is incredibly linear. We model it as P equals negative K sub F multiplied by X.
Okay, P is the resulting change in back pressure. X is the microscopic physical displacement of the flapper.
And K sub F is a massively large gain constant.
Because that K sub F multiplier is so large, it acts like a fluidic transistor. You move the flapper the width of a hair and generate a massive back pressure spike.
Which then routes into a larger cylinder to throw open a heavy industrial valve.
So we've got sensors reading reality, actuators ready to unleash fury. The final piece is the brain in the middle deciding how much fury to use.
The undisputed king of algorithms here is the PID controller. Proportional, integral, derivative.
I love the PID framework. It basically teaches a microchip how to experience the concept of time, the present, the past, and the future.
It really does. Let's break down how this digital brain thinks. The P is proportional control. It deals exclusively with the present moment.
So it just looks at the current error and reacts. If an industrial oven wants 100 degrees but reads 90, present error is 10.
The controller multiplies that 10 by a proportional gain setting and opens the gas valve. If error drops to 5, it cuts the valve halfway down.
Larger present error, harder it pushes. But relying only on the present creates a physical paradox, doesn't it?
Yes, as the oven heats up, the error shrinks, so the valve closes more and more. Eventually you hit, say, 98 degrees.
And at 98, the tiny error of 2 tells the valve to open just a tiny crack.
But that tiny heat perfectly matches the ambient heat leaking out of the oven door.
The system falls into equilibrium. It creates a persistent, steady-state error.
The proportional controller is totally satisfied, pushing just hard enough to hold 98. It will never, ever reach 100.
To break that equilibrium, we introduce the I-integral control, the memory of the past.
It's an automatic reset mechanism.
Yeah.
It continuously adds up or integrates the error over time.
It says, hey, error is only 2 degrees, but we've been 2 degrees cold for 5 straight minutes.
Exactly. It adds that error every millisecond. The mathematical sum grows larger and larger, forcing the controller to push the valve wider and wider.
Dragging the stubborn physics of the oven exactly to 100 degrees, eliminating long-term drift.
And finally, the derivative control, the prediction of the future. It analyzes the rate of change of the error.
So if the oven is at 80 degrees, but rocketing upward incredibly fast,
The proportional term is still screaming, add heat, we're 20 degrees away. But the derivative term looks at the velocity.
it looks at the future and says, if we keep adding heat at this rate, we're going to blow past 100 and hit 120.
So it calculates a negative control signal. It applies the brakes before the target is even reached.
Severely dampening the system to prevent a massive under-damped overshoot.
Past, present, future. Perfectly balanced.
Wait, I have to stop and unpack a massive caveat here, because the math of the integral term can actually cause the exact disaster it's trying to prevent.
Integrator windup.
Reset windup. The integral control fixes steady-state drift, but it's also the exact thing that causes a machine to lose its mind and violently overshoot when it hits a physical wall. How do you balance that?
Well, windup happens because pure mathematics has no concept of physical limitations.
Right, math just calculates numbers.
In a simulation, if an error is large enough, the PID can command an actuator to open to 500% capacity instantly.
But in physical reality, actuators saturate. A valve only opens to 100%. A DC motor blows a fuse if it draws too much amperage.
Let's map out a disaster. Imagine a drone holding altitude at 10 feet. Operator suddenly commands it to climb to 500 feet instantly.
Massive error. 490 feet.
Proportional term instantly commands rotors to maximum power. The physical motors are fully saturated at 100% capacity. Drone is climbing as fast as physics allow.
But it takes time to climb 500 feet. And during all those seconds, the integral term, the memory of the past, is rapidly adding up that massive error every millisecond.
The mathematical sum explodes. It winds up to a gargantuan number, mathematically commanding 3,000% power, even though motors are maxed at 100.
Finally, drone hits 500 feet. Present error drops to 0. Proportional shuts off. Drone should stop.
But the digital brain doesn't stop. That wound-up integral term is still sitting in memory, holding a massive positive value, screaming to keep climbing.
The drone violently blasts past 500 feet, climbs to 600, 700 feet.
Because it takes massive amounts of time for the drone to generate a negative error to slowly subtract from that gargantuan wound-up sum until it finally unwinds to 0.
In industrial robotics, that delayed overshoot shatters tooling. It destroys safety cages.
Which is why engineers write complex anti-windup algorithms that actively disconnect the integral math whenever they detect actuator saturation. The software must respect the limits of the brawn.
Which brings us to the final and maybe most deeply philosophical realization of this deep dive.
It's a big one.
We've architected everything. Critical parameters, Taguchi tolerances, jujitsu traps, dynamic models, tuned the PID brain, anti-windup precise sensors.
Yeah.
We are reading the state of the machine perfectly, except there is a massive catch.
The observer effect.
Exactly. The mere act of measuring the machine physically alters the machine.
It is the great paradox of mechanical control. It's the macro-mechanical equivalent of Heisenberg's uncertainty principle.
You cannot observe a dynamic state without permanently changing it.
Formalized in systems engineering as measurement impedance and static stiffness.
This is blowing my mind. Let me try to map it. If the digital brain uses an LVDT or pressure transducer, the sensor has to draw energy from somewhere to generate a signal, right?
That's the fundamental constraint. You can't measure an effort variable like force or pressure for free. The sensor siphons a tiny amount of energy out of the system to operate itself.
And the moment it siphons that energy, it alters the precise reality it was trying to measure.
Let's ground this with the classic example. Measuring the deflection of a massive steel cantilever beam.
Okay, heavy steel diving board bolted to a wall, heavy weight on the tip. We want to measure how many millimeters the tip bends down.
We put a standard mechanical dial gauge with a little plunger probe directly under the tip. The beam bends down, pushes the probe in, needle spins. Seems perfectly objective.
But it's mechanically subjective because to keep the probe extended, the dial gauge has a tiny internal spring.
With its own specific physical stiffness, which we identify mathematically as K sub m.
So when the massive steel beam bends down and pushes the probe, the tiny spring inside the dial gauge is actively pushing back up against the massive beam.
It's literally holding the beam up. The dial gauge is physically resisting the deflection it's supposed to be measuring.
You're not measuring the undisturbed beam anymore. You're measuring a hybridized system of the beam resting on the sensor's spring.
We use the compliance formula to calculate exactly how much the sensor is lying to the computer.
That's the magnitude of the lie. We write it as Q sub m equals Q sub u divided by the quantity 1 plus C sub go over C sub I.
Let's translate those variables. Q sub m is the measured value, the number on the dial.
And Q sub nu.
That is the undisturbed value, the true, pure physical reality of how far the beam would have bent if the sensor never touched it.
Okay, look at the fraction in the denominator. C sub go is the compliance, the bendiness of the original beam.
And C sub guy is the compliance of the measuring instrument, the spring inside the gauge.
If you analyze the math, if the instrument is infinitely soft, C sub guy is massive compared to the stiff beam, that fraction approaches 0. The denominator becomes 1.
And the measured value perfectly equals the undisturbed value.
Yeah.
But physical sensors are never infinitely soft.
They all possess stiffness.
If the instrument is stiff enough to push back, that fraction grows, denominator becomes larger than 1, and the measured value, Q sub m, shrinks dramatically compared to true reality, Q sub u.
The sensor fundamentally lies to the PID controller. Its very existence alters the physical brawn. It's exactly like Heisenberg's uncertainty principle, but for macro mechanics. The dial gauge is lying to you because its very existence changes the reality of the beam.
It's an incredibly humbling reality check. You do all this math, buy million-dollar grinders, tune your PID loops.
All to enforce absolute control over the physical world, and at the end of the day, your sensors can never truly know the perfect, undisturbed state of the machine once you touch it.
You can only model the energy transfer, bound the mathematically anticipated errors, and engineer the brawn to be robust enough to handle the inevitable chaos.
We've covered a staggering amount of ground today, pulled back the curtain on the invisible architecture between human desire and a vibrating piece of iron.
We definitely got into the weeds.
But as we wrap up, where does this leave us as technology evolves?
It raises a vital question for anyone entering the design space. We are accelerating into an era where machines are overwhelmingly defined by software, AI, and virtual simulations.
The digital brain is evolving exponentially.
But the physical brawn, the steel brackets, hydraulic oil, boundary layers, still obeys the exact same laws of thermodynamics and where it did a century ago.
The software might assume a perfect physical world, but the physical world always degrades. What happens when it does?
Exactly. As engineers spend 90% of their careers looking at pure code and pristine 3D models on screens, are we losing the intuitive, tactile feel for concepts like measurement impedance?
For critical parameters.
If a neural network optimizes a control loop based on a perfectly mathematically modeled world, What happens 10 years later when the real physical world inevitably vibrates, wears down the retard roll, or pushes back against the sensor? The CAD model is not the machine.
A perfect reminder that physics always gets the final vote. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.